So after having discussion about counters, we can take a look at other timer structures, right? So one of the timer structure is an interval timer. And what does an interval timer do? It indicates when desired time interval has passed. For example, if you're waiting for 20 nanoseconds and then you're generating an interrupt. So this interval timer would help you to delay till 20 nanoseconds and then you can generate the interrupt. Or an interval timer can also be used to generate an interrupt. Every 20 nanoseconds, when the timer overflows, an interrupt is generated. For that, we can set the terminal count to the desired interval. Right. So basically, this is a timer with terminal count. This is an up counter with the clock and the count. Now this is an comparator, right? And this is a register that holds the terminal count value. So for example, if we want to count till 200 clock pulses, so we set the terminal count to 200, counter starts at 0, and when this becomes 200, this becomes true, right? And the counter is reset and top becomes 1 to indicate that the counter has overflowed. So this is one of the methods that we can use. So number of clock cycles equal desired time interval divided by clock period. So how many clock cycles or what is the value of count? It's given simply by the desired time interval divided by the clock period. Then we can have cascaded counters. As we can see, this is a 16-bit up counter and the top signal is fed to the clock of this 16-bit up counter. So whenever the 16-bit up counter overflows, this 16-bit up counter is incremented by 1. So when cascaded, we can have a 32-bit counter output where the low 16 bits are given by this counter and the higher 16 bits are given by this counter. And if we can sever or remove this connection, we can use these two counters as independent 16-bit up counters. So this can be, for example, counter 1 and this can be as counter number 2. So this is very flexible. Last but not the least, we have a discussion about the prescaler, and like we discussed before, the prescaler divides the clock. And when we divide the clock, right, the clock frequency decreases, so time period increases and so range increases. But since time period, the numerical value of time period increases, the resolution in fact decreases. This is one point we discussed before. And this same discussion has been shown over here. This is counter 1 and this is counter 2. So lower 16 bits of the counter provided by counter 1 and higher 16 bits of counter provided by counter number 2. So this is an example of a reaction timer. This is a game commonly played by Air Force pilots. So when they want to test their senses, right? And what is the game? The game is very interesting. An LED indicator light is shown over here, and the rule is whenever you see the indicator light, at once you should press this push button. And this time is basically the delay between the indicator light showing and your response. So in Air Force, the pilots should have this minimum, this value minimum. This is the reaction time, okay? So we can measure time between turning light on and the user pressing the button. This is basically the fact, isn't it? We turn on the indicator light at random amount of time, and after that we time till the user has pressed the button, and this would give us the reaction time. So this is 16-bit timer. The clock period is 83.33 nanoseconds. This is given, and counter increments every 6 cycles. So since counter increments every 6 cycles, what is the resolution? Resolution is clock period multiplied by 6 or 0.5 microseconds. So since we have the resolution now 0.5 microsecond, we can find the range, which is 65,535 multiplied by 0.5. Why this value? Because this is a 16-bit timer. So it comes out to be 32.77 milliseconds. So we want program to count milliseconds, so we initialize the counter to this value. This is the total count that is possible, and this is basically the count that we require, which is 1 millisecond or 1000 microseconds. So we divide this 1000 microseconds that is required divided by the resolution. So this is the value that is loaded. What does it mean? So we load this counter with this value, and when the counter overflows by 65,535, it means 1 millisecond has passed. So what do? We have defined this value in this constant variable, and then of course we can have this count variable over here, right? So what do? We wait random amount of time, we turn on the indicator light, we start the timer. So while the user has not pressed the reaction button, so if the counter has overflowed, we stop the timer and we again initialize this ms count to this value so that the next millisecond count cycle can begin. We start the timer and we reset the top signal and we increment the milliseconds. So again, if the top signal is received, right, this loop would be true while the user has not pressed the button, right? So every time the counter overflows, we are going to be having this particular arrangement, and this millisecond would be incremented. So when the user presses the button, we turn the light off and we print this number of milliseconds have passed. So this was an example about reaction timer. Now we can look at the watchdog timer, which is a very useful timer, right? Watchdog timer has got many applications, right? One of the applications being that it can be used for certain interrupts, right? Like it has been shown that we might set the watchdog timer to disable itself after 100 milliseconds, or in other words, if the watchdog timer is not disabled within 100 milliseconds, the watchdog timer would generate an interrupt. So that is the idea. So watchdog timer is the timing device that is used set for a preset time interval, and an event must occur during that time interval unless the device will generate the timer signal on failure to get that event in the watched time interval, right? So watchdog timer has got many applications. For example, watchdog timer can be used to debug softwares, okay? So that is one of the reasons that can be done. One of the watchdog timer applications has been shown in this figure. So we have the CPU that is executing some instruction or some operation. We have this watchdog timer which is running separately. So one of the important points about watchdog timer, it's a free running oscillator or a free running timer. And what do we mean by a free running timer is that the watchdog timer has got its own clock source. So in other words, the watchdog timer can run whenever if even the other system is not running. For example, we might have the CPU which has been put into sleep mode or hyper sleep mode, right? So in that case, the main clock of the CPU has been stopped. But the beauty of the watchdog timer is that the clock source is separate for this watchdog timer. So this watchdog timer can operate even when the main CPU clock has stopped. So what is the benefit of this? The watchdog timer might generate an interrupt that might allow the CPU to wake up from sleep. So this is one of the applications that can be had of the watchdog timer. Another application of a watchdog timer can be to troubleshoot your code, right? Let's see, the watchdog timer is set to generate the interrupt signal in 100 milliseconds as it is shown. Okay. So what happens? The CPU performs code, and well before 100 milliseconds, the CPU executes the clear watchdog timer instruction. And clear underscore watchdog timer instruction, what does it do? As the meaning shows, it sets the watchdog timer to 0. Remember, watchdog timer is an up counter like other timers. So the CPU would periodically keep executing the clear underscore watchdog timer. So under normal circumstances, when the CPU executes clear underscore watchdog timer instruction well before 100 milliseconds, the watchdog timer cannot overflow and the watchdog timer cannot generate an interrupt signal and interrupt the CPU. So what happens if the interrupt is generated by the watchdog timer? It means that the code of the CPU was stuck at some point, so that it could not execute the clear underscore watchdog timer instruction in real time. That's why the timeout or interrupt occurred. So these are some of the applications of the watchdog timer. So again, like we discussed, with the timing device that is set for a preset time interval, right? So this preset time interval might be 100 milliseconds. So like it is said, like I discussed in my previous example, if well before 100 milliseconds, for example, right, the event occurs, the watchdog timer would be disabled to disable generation of timeout or reset or an interrupt. Okay. So timeout may result in processes start a service routine or start from the beginning. So if the timeout occurs, it means the watchdog timer has overflowed and has generated the interrupt signal for the CPU. So this again diagram shows the application. So these are the lines of code that is happening, and we always execute the reset timer instruction well before 100 milliseconds, like I discussed before, by using the clear watchdog timer instruction, right? So if the clear watchdog timer instruction could not be executed on time, the watchdog timer would overflow and interrupt. So for example, if we anticipate that a set of tasks must finish in 100 milliseconds interval, right? So the watchdog timer is disabled and stopped by the program instruction in the case the tasks finish within 100 milliseconds interval. Okay. And if the task is not finished, so the watchdog timer is not disabled by the program instruction, watchdog timer generates interrupts after 100 milliseconds and executes a routine which is programmed to run because there is failure of finishing the task in the anticipated time interval. So since the task could not complete in 100 milliseconds, the watchdog timer interrupt occurs, which executes a ISR or interrupt service routine. So that's how the watchdog timer operates. Another very important use of the watchdog timer is in generating power saving delays. This is yet another interesting application of the watchdog timer, and basically watchdog timer can be used to implement power efficient delay in the embedded system. So let's see what it means. This is basically, the first code is basically the usual delay version. We have a main function, and then we have a super loop in which we execute the delay function, which delays for specified interval of time. After that we have that other processing. Now the main point or main disadvantage of this approach is, if we only have to wait and do not do any other processing, so we are executing instructions at full clock frequency. So when we are executing instructions at full clock frequency, we are wasting time and we are wasting energy, right? So the other method is basically we can have the power saving version. In the power saving version, we make use of this watchdog timer to generate the delays. So one of the methods can be that we come over here, we execute the super loop. Now we set the watchdog timer for the specified delay. For example, if we want to delay for 100 milliseconds. So we set the watchdog timer to time out after 100 milliseconds. So we start the watchdog timer, then we go to sleep. So basically when we go to sleep, we are saving power because all the circuits are powered off for by this particular sleep instruction. Even the main clock of the processor is stopped. So once the processor is sleeping, which event would wake up the processor? The watchdog timeout. So whenever the watchdog timeouts after 100 milliseconds, it would wake up the processor. The processor would wake up and start executing from this point onwards. So we have a delay, but we are not executing instructions in the delay. We are just sort of sleeping, which is basically a lot of power saving that we can do. Now we look at another application of watchdog timer, which is basically an ATM timer, right? And what is the ATM timer? When we don't press any key on the ATM, right, the timeout, or we are inactive, right, so the transaction is cancelled after 2 minutes. So this is basically our ATM timer. So whenever we are pressing any key on the ATM pad, we are basically resetting the watchdog timer so that the reset does not occur. So what is the common use? It can detect failure or it can use self reset. So when we are working with the keypad of the ATM, we must reset the timer every X time unit, else timer generates a signal, right? So what are the other uses? Timeouts in the ATMs. So we have this oscillator, we have a prescaler divided to OSC, so we have the clock, then we have the scale register, which when overflows ticks the time register, and time register has got a check register value which is compared, right? So if the time register tries to have more value than check register, the overflow signal would be generated, or a system reset or interrupt would be fed by this overflow signal, right? So what we can do, we can have certain calculations. Let's say the oscillator is 12 megahertz, and prescaler is equal to 12, right? So what is this clock? Clock equals oscillator divided by prescaler, which is 12 divided by 12 equals 1 megahertz. Right? And so what would be the time period for this clock? Time period for clock signal is 1 over 1 megahertz. So time period for clock is 1 microsecond. Now it's given that the scale register is 11 bits and time register is 16 bits. Okay. So now if we want to find out the range of scale register, right? So what would be the range of scale register? Range of scale register would be 2 raised to power 11 into this T clock, which is basically the resolution of the scale register. So range of scale register equals 2 raised to power 11 into 1 microsecond, which comes out to be about 2 milli seconds. Now range of scale register equals resolution of time register. Why? Because when the scale register overflows, it increases one value of the time register. So range of scale register equals resolution of time register. So please write it down. Range of scale register equals resolution of time register. So what would be the range of time register then? It's going to be 2 millisecond, which is the resolution of the time register, multiplied by the maximum value, which is 2 raised to power 16 minus 1. That would be the total in milliseconds that we are having, right? So of course, when this value overflows from the check register, then the overflow signal would be generated. So the main point is which value to load in this check register so that the overflow can take place. For that matter, we can have this formula. The time register value equals 2 into 2 to the power 16 minus 1, which is the range of time register, minus a value of x. X would be the value that would be loaded, right? So it is required that we need a 2 minutes delay. So for 2 minutes, what is 2 minutes in milliseconds? It is 2 into 60 into 1000, which is 120,000, right? So what should be the time register value? The time register value would be 131070 minus 120,000, which is the value of x. So the value of x to be loaded would be x equals 131070 minus 120,000. So this is basically your answer for this particular application, right? On the right hand side we have this code, right? This is the main function, right? Wait until card is inserted, and we will call the watchdog underscore reset underscore routine. So while the transaction is in progress, if the button is pressed, we'll perform the corresponding action and then we'll call the watchdog reset routine. So if the transaction is in progress, right, and the watchdog reset routine is not called every less than 2 minutes, the interrupt service routine is called, right, because the watchdog timer overflows and it interrupts. So if this is not the case and the watchdog timer is not overflowed, we come over here, which watchdog underscore reset underscore routine, and check register is set so you can load the value into the time register, right? This check register is set to be 1, scale register is set to be 0, and time register value has been moved to 11070. And what happens if this watchdog underscore reset routine cannot be called? We call the interrupt service routine, which ejects the card and resets the screen. So that is all about the watchdog timer application.